Now let's talk about the topic of static analysis. What do we mean by static analysis? As you can imagine, static is something that's stationary, it is not really moving. So I'm using it in the context that it is opposed to dynamic, which is what actually happens when the program is running, right? And this is a sort of common scenario that, common context in which the word static is used over here, right? One way of looking at it would be that we are basically looking at things that can be done at compile time, right, before you actually start running the program. And why is this important, especially in the context of embedded systems? Because of the way embedded systems work. Unlike, let's say, something like a payroll program, which you write out a program, it runs the logic once, and then that's it, you're pretty much done. Unless, of course, you need to run it again and again and iterate. It's very often quite possible that a number of programs that you write just run once and finish. Right? Embedded systems are the exact opposite, right? You really don't care about you possibly don't care about how long it takes to run once, because the main thing is that it is running repeatedly. Pretty much you switch it on, and then unless something drastic happens, you are not expected to switch off the system at all, right? So it makes sense to put in a lot of effort on optimizing the system as much as you can at compile time statically, right, without running the program, and try and eliminate as many bugs and performance related issues as possible at compile time itself. This is basically what static analysis refers to. It can help you to identify potential problems. These could either be bugs, which are outright errors in the code, or it could be a stylistic error, or following certain kinds of recommended practices. It could be performance related, right? All of these certain kinds of tools are sort of specialized for detecting them as early as possible, and the way that they work is they are usually sort of supplements to your compiler, right? The compiler has the ability to detect certain kinds of issues, and what you do is you use these extra tools, which are sometimes called linting tools or other kinds of static analysis tools, which will alert you to potential problems at an early stage. Now, just to take a concrete example, right, let's take this particular code that we have. It's of course an extremely trivial code, it doesn't really do anything. All that I'm doing is I'm basically just declaring a pointer, allocating memory to it, and then I return, right. Now the point is that strictly speaking, this, you may argue that this is not really a bug, because after running over here, I return and exit the program, and once the program has exited, then pretty much the memory has actually should automatically get freed. Now in the context of an embedded system, for one, that may not always happen, right? I typically don't have a main function that exits. Instead what I have is I have some kind of a thread which gets initiated and then is just permanently running, right? So if I have memory of this sort that is not getting freed before a particular function exits, right, it is quite possible that it actually sits over there and the compiler does not automatically figure out that it has gone out of scope and free it. The only time it actually gets freed is when the entire program exits in the first place, which doesn't happen in the context of embedded systems. So the question is, the C compilers by default can be very forgiving, right, which is not necessarily a good thing, right. There are ways by which you can sort of specify certain flags to tell the compiler to be strict and indicate errors rather than just sort of letting such things pass by. But there are also sort of variants on the compiler, and if you think about it, right, I mean, it is the compiler's job to pretty much catch anything like this. And what we have is that there are tools which work as sort of components of the compiler or parts of how the compilation process works, and are able to sort of indicate problems like this for you, right. Now as an example, once again I'm just going to show you a small piece of code that runs on a regular Linux based system. So let's look at the same code that I just showed you a moment ago. What we have over here is there is this a main function where a pointer is declared, malloced, in other words dynamically some memory is allocated to it, and then the function just exits, right. Now as the comment over here indicates, this is a potential memory leak, free is not called. Now in practice this is probably not a serious leak for the simple reason that the function, the program itself is exiting. But as I said, if this had happened in some other function which was there inside a larger program, then this would actually be a potential memory leak, right. Now let's look at Clang, right. Clang and GCC are two of the most well-known compilers in existence today. GCC is the GNU compiler collection or the GNU C compiler, which is probably the older of the two. It has been around since the mid 80s or so, undergoing various developments. It is it's probably the best known open source or the free software compiler that has been around for a long time. Clang is a compiler that is built on top of the LLVM infrastructure, the low level virtual machine project, which is actually a very sort of interesting and powerful a set of tools that can be used actually to build various kinds of compilers and optimization infrastructure and so on. For our purposes, we are going to use Clang with a flag that is called analyze over here, and I am just going to call it with this program that you see above, right. Now let's see what happens when I just give Clang the analyze flag and ask it to look at this program membug.c. It's not actually going to compile the program for you, but it is going to sort of give you some kind of warnings. And in this case you can see that there are basically these two warnings that come up. One of them, it says that the value stored into PTR during its initialization is never read. Now that's interesting. Basically what it says is you have taken the value, you have declared a variable, you have stored a value into it, and then you don't have any other code in your program that actually uses the value of PTR. This is an example of what is called dead code, right. So it's essentially telling you that the code exists. If you ask the compiler to compile it, then yes, the compiler will probably generate code for you to do the malloc and so on, but it's dead code, it does not have an effect, right. And in the higher optimization levels of any compiler, usually dead code is just eliminated. So it's entirely possible that the compiler, if you actually ask it to compile this, would just remove this malloc altogether, right, because you never make use of it. The second one, it also says that there is a potential leak of memory out here, right, and that's exactly what we said, because you are returning at this point without having freed PTR, right. If you think about it, this is a slightly strange error message. It's telling you that it's an error related to unix.malloc. Ideally it should just have told you that hey, you had a malloc without a corresponding free, right. Instead it says there's a potential leak of memory, and as long as you know what a leak of memory means, that should be enough to alert you to the fact that you need a free somewhere in your code. Okay. So this is again an example of what can be done with static analysis. Okay. Now what I'm going to do here is just sort of quickly run through a largish number of examples of potential problems in code that could be caught by static analysis. The set of examples that I am showing here are by no means exhaustive, right. Compilers look at various different kinds of rules and say, okay, what is and is not potentially a problem, right. So what I am showing over here is just some classes of potential fairly easy to identify problems that you need to be aware of at least. One of them is of course the memory leak itself, right. We basically sort of declare a pointer, in fact you assign a value to it in this case, and then we don't have a free out here. Now this could be legitimate because it might be that this whatever you allocated using malloc is needed somewhere else in some other part of your system. Practically that's a little difficult to understand because of the way that this code is written, because I have declared int star ptr only here, right, which means that PTR is not even visible outside of this function. But if for example I was to return PTR, let's say that this was of type int star and I returned PTR, then it suddenly becomes valid to actually have this code right? I won't have the free PTR out here, and I must actually take care of freeing it somewhere else in my system, right? But as it stands, this is a memory leak because I have declared a pointer, I have assigned something to it, and I have not freed it, and at this point, the moment I exit this function, PTR no longer exists, but the malloc was never matched with a free. You can have things called buffer overflows. In this case, I have declared a char buffer of 5, and I have just given this function string copy, and I have given it a string over there which is much longer than 5 characters, right? It turns out that the strcpy function, which is available in the C standard library, is not very smart about this. It will basically go in there and just try to copy this entire string into buffer of 5, which means that it will basically put in THIS space. You have run out of characters in your buffer now, but it will continue. The IS space TOO and so on will continue into the next successive memory locations. That means it could end up overwriting some other variable that you have defined, right? And in general, this is exactly what is meant by a buffer overflow. Now, there are modern variants of C, and the C libraries come with a number of other variants of these functions, right? There is strncpy where you can specify the number of characters to be copied and so on. And in general, it is always preferable to use a safer variant of a string copy command rather than just using something like this. You have to be extremely careful while using these functions, because it's very easy to create a really dramatic bug in your code by missing out on something very simple like this. Uninitialized variables, right? You have something where I declared x and I return x. In other words, I'm making use of it, but I never assigned a value to x, right? So what is going to come back out of this function is basically undefined. It could be anything. Dead code, we already saw an example of dead code, but I also have this thing where, for example, I could have if conditions of this sort. These, if you look at it, if condition else, so all possibilities are already taken care of out here. This print statement should never be reached in practice, right? So it basically becomes dead code. Resource management, if you could have a scenario where, for example, you basically declare a file, you open the file, you do something with it, and you finally return the file, but you don't have an fclose at any point, right? So you have basically got this file pointer through fopen, you return the file over here. Now, is this a bug? That's not entirely clear. It is quite possible that I actually want to send this file pointer to some other function, and hopefully I will fclose it somewhere else. But unless you actually keep track of that, it is quite easy at this point to miss out on fclose at some other stage and basically leave your system with a file that has been opened, maybe partially written to, and never formally closed, so that you can't be sure that the data actually went into it as expected. This is a slightly more subtle kind of a problem. What we have is there's a global variable which I'm calling as a shared variable, and I have a function out here which increments that variable. Now, the interesting thing is, by itself it looks okay. I just have a function that increments the value of a global variable. Where it gets interesting is if I have multiple threads or tasks in the context of embedded systems that could potentially access or call this particular function, right? Now, depending on the order in which different tasks are executed, I could even have a scenario where I try incrementing the variable, and the order in which I run it, in the worst case scenario, I could actually have a problem where, between the time that I read the value of shared variable, increment it and write the value back, the other thread has also come in, right, has sort of interrupted or changed my context of code, and therefore whatever I had read versus what I increment ends up being seen as a different value and therefore does not update as expected. That is the worst case scenario. The other possibility is simply because of the fact that different threads could basically call this function in different orders. What you see in any given thread could be dependent on the order in which you have actually run the different functions. So essentially code like this is considered as not thread safe, right, and that's the main thing which you need to keep in mind. Null pointer dereference, this is again standard problem with code. I have declared a pointer, in fact I have explicitly made it null, but then I try assigning something to it. This is equivalent to saying write the value 10 into memory location 0. Now in practice 0 is usually considered a reserved memory location just so that you can make use of the null pointer, and on any C based system pretty much this would be considered dereferencing the null pointer. It would be a problem. It means that you are trying to write something into memory location 0. Technically that is okay, it might even be possible to write something into memory location 0, but in practice it is almost always an error and is going to end up either crashing your program or causing some other kind of undefined behavior. There are problems called use after free, where as you can imagine I have allocated memory, I have freed a pointer and then I try to make use of it. This is not exactly the same as a dereferencing a null pointer, because at this point in time I have just freed it, which means that it's no longer allocated to my program, but PTR might still be pointing to a valid location in memory. So I will try to write something into it, I might even end up writing something, but for all you know that has now been allocated to some other dynamically allocated pointer, right, and I might end up overwriting some data that I should not have access to. Integer overflow is again, all of these in other words are things that can be fairly easily picked up by compilers. Integer overflow, let's say that I have a variable that has already reached the maximum integer value and then I add 1 to it, it can actually go out of scope, out of the range and basically become a negative number, right. Now this is a very unlikely practical scenario, but it is quite possible that a static analysis tool would actually be able to at least warn you of scenarios where adding the numbers that you are doing could potentially go out of range and could overflow. That's pretty much all that it can do. And of course similar thing could happen with division by 0, right, depending on the value that is actually passed into this thing, you could end up having a division by 0. Now will this necessarily be an error? This depends, these kind of things depend on the flags that you have set for your compiler, right. Should you even flag this as an error, or should you just say, hey, we'll assume that the user knows what they are doing, right. So as you can imagine, many of these things are things that could outright be errors, like using a pointer after freeing it and so on, or it could be something which is perfectly valid code like division by 0 in this case, right, where it basically says it's up to the user to make sure that they don't pass a 0 as the denominator. Okay. A static analysis tool therefore is not necessarily going to give you compiler errors, it might even just give you warnings and say this is not a good way of writing the code. So there are code checkers. I already showed you an example with Clang, right, it's a compiler toolkit with support for static analysis. There is another open source tool like this called cppcheck, which does a good job of basically checking for such things. There are a number of commercial tools that are available, including Coverity, PCLint and so on, some of which are platform specific, right. So for example, if you have the specific type of ARM microcontroller, you might find that there are tools that work for that particular system or are provided by that particular vendor. In a lot of cases, these also take care of compliance with specific coding standards, right. And coding standards are an interesting sort of evolution of sort of design patterns at some level, right. Basically what they say is these are recommended ways of writing code in such a way that it is generally been shown in practice to reduce a certain class of errors. The most sort of well known among these is the so-called MISRA standards, right, Motor Industry Software Reliability Association. These are guidelines that are aimed at C and C++ development, and they are widely, even though they were primarily come from the motor industry software background, they are widely applicable across many classes of embedded systems, right. There are standards for C as well as for C++. And what they do is they basically provide certain kind of rules for how the software should be written, right. Certain kinds of rules are mandatory. If a mandatory rule is violated, that's straight away the end of the discussion, right? I mean, you are not MISRA compliant. That's the end of the story. There are certain things which could be what are called required category of rules, where once again normal behavior would be that yes, this is also required, it has to be satisfied, but if you are able to provide good documented justification for why you are violating this rule for your particular project, it will still be considered compliant. And there are others that are just called advisories, which are more like best practices. They say, okay, ideally your code should look like this. If it doesn't, then that's still not going to be flagged as an outright violation of the standard, but you should try and fix it if you can, right? Now, where this really becomes important is that because of the amount of time and effort that has been put in to actually create these standards, they are well regarded in terms of how they help to eliminate certain classes of bugs, and a lot of industry, especially government, space and other kinds of safety critical applications, they actually take MISRA coding standards as a requirement for many of their for a lot of the code that is used in such systems. Now, an example of what MISRA could look like could be as simple as this, right? What it says is this is purely stylistic. If you think about it, this is not really wrong code, except that because if you look carefully at what is happening in this part of the code over here, you will notice that because of the semicolon that is present at the end of this for loop, what is actually going to end up happening is x plus equal to I is not actually running as part of the for loop, even though it looks that way because of the indentation, right? And because of that, MISRA actually says that x, any code that is inside the for loop has to explicitly be put within curly brackets, right? The C programming language compilers in general say that the curly brackets are optional. As far as MISRA C is concerned, they are not optional, they are required, right? So this is just a very small example of the kind of rules that would be enforced. As you can imagine, many of the rules like this are easy to automate. You can just have a automated program that would run through your code and tell you whether you have violated any of the MISRA standards or not, which means that sort of finding and fixing those should be a relatively straightforward thing to do, although it may end up being time consuming at times depending on how well you have been writing it in the first place. So to summarize, the whole point of static analysis is to try and catch bugs as early as possible, and it's especially relevant for embedded systems. Why? Because they have resource constraints. Very often they are being applied in safety critical applications or areas. You want predictability, right? So that several classes of undefined behavior can be eliminated. The other thing where you want this kind of static analysis is simply from the point of view of maintenance, right? How do I have code that others can read and be able to contribute to, either in terms of improvements in functionality or even just fixing bugs. And as I said, MISRA is sometimes considered as a compliance requirement. There are agencies, especially government related or possibly space or defense related, where this is actually a mandatory requirement. You need to have certain kinds of MISRA compliance for your code to even be acceptable for basic review.